So this is lecture 8, module 2, and then in the last module we talk about basics of k-nearest neighbors, and now I'm going to generalize from just k-nearest neighbor to a little bit more called instance-based learning. So we talk about in the k-nearest neighbor, and it's the basic assumption is local smoothness, and we're using training sample as our model. So what do we mean unit training sample as our model? So this actually reflects a bigger group of method. And we are also, like I try to emphasize, we're actually moving to this classification section. And the instance-based classifier is one of the big groups of classifiers, and in the literature we can actually group all the supervised classifiers into 3 groups, and the first group is discriminative classifiers, and the main goal in the discriminative classifiers is to directly estimate decision boundaries. All right, so this is the reason why I try to emphasize this definition of the concept of decision boundaries. So when we have 2 classes, rather than learning the class 1 and class 2, like this positive, we don't actually need to worry too much about very dense positive or very dense negative. What we need to model to make a good classification is to get that decision boundary. And this group of method is focused on getting a good decision boundary. And you can group like logistic regression, nearest neighbor based class, not nearest neighbor, logistic regression, neural network based classifier, and support vector machine decision trees. They're mostly belonging to this group. And in essence, what they truly model is this. It's P-Y conditional on X. So this is in the probabilistic sense. That's the true definition, discriminative classifier. But intuitively, you can think about is this group focus on modeling the decision boundaries. All right, so this is the first group, and that's exactly this next section we're going to talk about. And today and the next lesson are the last two lessons in the section 1. And then the second group is called generative classifiers, and this group of classifier actually cares to model this. It's P X condition on Y. Y is a specific class. So this maybe sounds difficult for you, but you can think about like this in this example. So we have this positive and negative. So rather than to learn this decision boundaries, I'm trying to fit very good density estimation to model my positive class and to model my negative class. So that's the basic idea of generative classification models. Yeah, all right. And those will be the third section we're going to focus on, and after the next section, which will be logistic regression and deep neural networks. And today we're finishing the third instance-based classifier because this group is extremely simple and intuitive. All right, so this is about the bigger picture, where we are. So let's now look at more details of instance-based classifier. So this is like a repetition. So again, 3 groups: separation boundary, generative, local smoothness-based instance classifier. And in the next section, the beginning class, we're going to talk a little bit about metric. When we talk about classification, we're not using the same kind of metrics we use as the regression model. So in your homework 1, we ask you to report the mean square error. So again, when we talk about mean square area, this is about a metric to evaluate how your model behaves. So don't get that confused with your gradient descent implementation. And I don't understand why some of you got confused, because maybe you already start to touch PyTorch or those libraries. They actually use there's because normally in PyTorch they have a loss function definition that you can directly use the gradient descent from that loss module. So we're going to talk about those in the third homework. So it's not for now. For now, separate everything we talk about that get loss function. It's about the evaluation, and you implement your gradient descent in a separate function. Yeah, don't use that get loss function. All right, so that's to try to clarify our implementation. Yeah. Okay, so what is instance-based learning? So this is the simplest form of like machine learning. The training instances are just searched for the neighbors in the end, for those who are mostly closely resemble this new X question mark. And every knowledge we assume, the instance themselves represent the knowledge. And the fundamental assumption actually is about the metrics. So your distance metric defines what's truly learned, because that defines the neighborhood, right? And everything here is about the local neighborhood is your model. So that's why what defines the local neighborhood is what you're learning. So instant-based learning is called lazy learning. And what we covered, so their instant-based learning, like we only cover k-nearest neighbor algorithm. And there's in the regression, there's a very famous method called kernel-weighted regression models we did not cover. And it's also used a lot in the case-based reasoning in those not traditional AI-based systems. This is the most fundamental approach, instant-based learning examples. And in more advanced deep learning, in the more deep learning current research, there's something called a metric learning. Or maybe deep metric learning. DN-based metric learning. So they're basic metric learning. There's also deep neural network-based metric learning. You can think about is it really tries to learn really good similarity functions. Oh, distance function. Based on data. It just, you learn it. What is the best function from data? But that's not what we are going to cover today. So what we're going to cover today is what makes an instant-based learner is the most important is there's a distance metric. You actually can learn it from data, but in the vanilla k-nearest neighbor method, you as a user, you define it. So there are many different kinds you can use, right? We already showed you a few cases, like in the maybe minus the inner product, minus the cosine, the most popular and basic Euclidean distance or weighted Euclidean distance. And there's also popular distance metric like L1 norm, L-inf norm, Mahalanobis based distance, correlation, angle, Hamming distance, especially Hamming distance. So if you think about string search, we actually talk a lot about this, the string search, and or maybe even the whole Google search, the vanilla version. So in fact, I mean, in the beginning of this type of retrieval engines people use a lot, they normally use cosine distance on the vector space or the string-based Hamming distance on the query space. And those are instances of k-nearest neighbor. And k-nearest neighbor is the most fundamental, simplest approach, but has fundamental, profound impacts in actually everything we're using now. So of course, what we truly use now are much more advanced version, has a lot of flavor with this deep neural network-based metric learning. It's not just user-designed string search, but the basic algorithm is actually there. I mean, so keep that in mind. It's simple, but extremely powerful. In this type of user-defined distance measure, the reason why I'm explaining this because this is homework 4. So I push the k-nearest neighbor-based implementation. It's normally in the homework 3 because this year I make the deep learning homework first. So I push k-nearest neighbor-based into the homework 4. So everything I talked here, you actually need to be mindful in your implementation in homework 4. So that's the reason why I talk about this. All right. So when you handle data in the basic k-nearest neighbor method, you need to be careful of the scales of your features. So let's just see most basic k-nearest neighbor Euclidean distance-based calculation. You really just, this is xi, xj samples. Let's use the sub maybe, yeah, the notation really confuses you. So let me just use maybe I feature, let's me f, to represent different features. So we need to calculate, so yeah, just minus in the product, assuming. So we're doing really, assuming it's the minus, it's a negative inner product. It's really simple to calculate inner product. So minus summation of f from 1 to p features, or maybe k seems to be more natural here, and then is the xi is my xi sample, it's k features, it's multiply. Yeah, it's actually multiply. Yeah. Okay, let me have, yeah, okay, inner product is fine. So xj and case feature. All right. So let's see if your height is 1.5, 1.8 meter, and it's one feature. So this is the k to 1 feature. This is k to 2 feature, and this is k to 3 features. If I'm doing this operation and doing the income feature, k to 3, because it's a much large number, will dominate in my inner product. So it doesn't really matter the height or weight, no matter how large they are, because the number just in this income dimension is just so large and dominating. So it's usually when you use this type of calculation, you need to be very mindful in terms of the scales of your features. So a good practice people do is to normalize the feature. There are different kinds of normalization. We will talk about that later. There will be clear instruction in the homework, but just for now, you can do like normalize it into mean 0, variance 1, or you can also just scale the feature by its max number minus mean number, so which makes it into a scale 0 to 1. So there are a lot of different methods you can use, but keep this in mind. Scale of your features need to be comparable, yeah, just to not mess up with the metric calculation. All right, so, and then the next question is how to pick the k. So again, the simple example is 1k equal to 1 in this one. You got, so the prediction will be actually sports. If a k equals to, I think it's 2, it's actually very hard to decide in, it goes to science. It's blue color. Yeah. And then k equal to 3, it's actually even more dramatic. This gives me sports. All right. And then 5, I think this is still sports. All right, okay, so let's again just show you this figure we get. If you are nearest neighbor in doing the regression, you got a super wiggling line. If you kick to 100, you got very smooth prediction to correlate the x and the y. So let's think about if k is too small and your regression for the future points will be super sensitive to the noise points. And just a little bit differences in your training data, it will make the whole boundary very change so much, a lot. And the k is too large, and your neighborhood may include points. So just you really very little. If you look at here, so this very smooth, but is this a good one? It's hard to tell, right? Because it just predicts so badly on the points here. And I think mostly it's on that point. It just predicts really badly in that region. So what should you do? I think I already have a calculation. So I think what I want to say is just you do k-folds cross-validation, or when your training data is a lot, reference data is a lot, you do you do training validation and test split. So now I want to put like all 3 different kinds of models we learned so far all together. So the first kind is the polynomial model, polynomial regression model. The second kind is this ridge regression model. And the third is this today what we learned, k-nearest neighbor based, because they are all regression. Let's just do regression. So if you still remember, for the polynomial model, its hyperparameter is d. Oh. Yeah, I still want to do from the scratch. So its hyperparameter is that d is the highest polynomial term. And in the ridge regression, it's lambda. In the k-nearest neighbor based regression is k. This is hyperparameter. So, and in all this type of models, and there's a concept called model complex and model less complex. So let's just see, let's use this more coordinates. It's less complex, and on the right is more complex. So very complex. So what I want to actually more look like a test you is, so for D, is it small on the left or it's large on the left for the polynomial regression? So feel free to type in the chat. So when D increases, my polynomial regression gets more complex or less complex? Yes. So when D increase, I'm more complex. When D is small, I'm less complex. So it's more like in the small case, I got like flat model. In the large case, I got really wiggly regression model. Perfect. And in the regression case, lambda, so in lambda become what makes the ridge regression less complex? Is it lambda large or lambda small? Is lambda 0 or lambda infinity? So remember, lambda is a positive number. So this is very important. So when lambda close to 0, my ridge regression is more, so lambda representing the shrinkage, right? Remember the shrinkage concept. When lambda is more, it shrinks more. When it shrinks more, it means what? When it shrinks more, it means less complex. So yes, perfect. So which means what? When lambda, oh, so for the less complex model, lambda actually is very large. So for the more complex model, lambda, it's actually small. So it's this one close to 0, this close to infinity. And so in the case, it's, so this is, if you, of course, ridge regression is a wrapper. It's wrapped on top of the maybe polynomial regression, maybe RBF basis regression. So it can be, if you still remember, when lambda is super, super small, you got this super wiggly bell fitting. When lambda is really large, you got this very nicely signed fitting. Yeah, so that's the example we showed. Okay, so now let's do the k-nearest neighbor case. So it's k large means less complex, or it's k small means less complex. My k-nearest neighbor decisions. My k-nearest neighbor k. So it's smaller k means more complex model, or it's smaller k means less complex model. I know it's very confusing, but this is important. Yeah. Yes, small k is more complex. So we can use a k classification to show you because it's a little easier. So like I have like this type of thing. If I have very less k large, so this is like a k very large, I will got very smooth boundaries. But if my I still like this exercise though. So if my k is, let me put here, just to make it very apparent. K small, so no, it's k small here. K is small, 1k is large. And then if 1k is small, I got a super wiggly decision boundaries. And just make it more dramatic, in this case, I got this. Too bad. I cannot change the color, but you get the idea. Yeah, k large, and so this is for k-nearest neighbor, this is for ridge regression, and so this is yeah, all right, so you get the idea. Okay, I will put a little blue color next time. Okay, so I think this is so there's a little more, but it will be covered more in next class called bias and variance trade-off. So what I just showed you, this polynomial d changing and k changing and lambda changing, it really tells you something. You actually can control the complexity of your models. And so in the k-nearest neighbor case, when you versus a linear decision boundary and you have this global model, very stable, but it can be inaccurate. And we call this type of model low variance, high bias. And on the right, this kind of one nearest neighbor approach is very local, very accurate on the training data, but it's like unstable. So we call this type of model low bias, high variance model. All right. So bias variance trade-off is the most fundamental principles inside machine learning, and we're going to talk about that and how do you, in different cases, how do you control it? And there are a lot of strategies you need to learn how to control bias variance trade-off, especially in the deep learning when you work with deep learning models, because those type of models are normally in here. So majority of deep learning models, they have low bias and high variance, so that you can call this overfitting. They have overfitting problems. And the left, this is called underfitting. Underfitting means both train and test has high errors. Overfitting means training is really good, almost no error, but there's high test errors, high generalization errors. All right. Okay, so yeah, I kind of repeat smaller, so, yeah. Smaller k is large variance and larger k is large bias. Yeah, so smaller, like the large variance give you unreliable estimation. So large bias give you inaccurate estimation. Yeah, keep that in mind. One is unreliable, one is inaccurate. So this is another way to talk about this. One is, so this is like overfitting, and the under is underfitting. All right, inaccurate, underfitting, unreliable, overfitting. Okay, so there's a little bit like variation about this kind of instance-based learner. Is people just not directly using the distance to make a judge for the predicted y. They actually revise it by using the distance. So for example, I actually can vote my votes from my neighbors according to the distance. So this is the simplest way to do this, right? I'm going to weight the different points using this 1/d quadratic term. So for example, in the regression, if I use this term, I will equivalent to, so this is almost exactly is the weighted kernel weighted regression formulation. I will consider closer points decision more, I weight them more, and I consider this far away points decision less, and to influence my prediction. That's all about it. Yeah. So there's some extreme options. People actually have this. Maybe you can treat this called a modified Shepherd method, and it has very popular uses in the geospatial analysis. And this type of k-nearest neighbor approach, again, so simple but very profound, and they made very profound impacts in the internet, in many natural science. Okay, so another way to do the weights is our old friend kernel, this RBF-based kernel. So we can again calculate bell shape, and the bell is using one of the potential training data as the center, and you can use design the lambda to control the wideness of the bell. And then I'm just make my prediction. This is a classification case. I'm using my prediction as a weighted of the class labels, and then normalize it into, so this, and this makes sure this is still look like a probability, which means what? Which means summation of p y from class 1 to class C, condition on x equals to 1. So let's just see from 1 to capital C. Yeah, so the reason why we do this normalization is to make sure this still look like a probability. All right, so you get a probability vector from the prediction. All right, so so this is almost it. So for the regression case, you can do the same thing, and the only thing you change it is just y prediction equals to summation wx xi, and each xi as the center, and then just time that yi over summation wx xi. Yeah. This is a weighted version of k-nearest neighbor. This is, you can call this is actually the equation called weighted kernel regression, or weighted RBF regression in this case, because we are using RBF kernels. All right. Okay, so I almost finished the k-nearest neighbor and instance-based classifier, but I actually skipped something which is extremely important. So what did I skip is we actually emphasize when we talk about models, we aim for those models generalize well. and also computationally scalable and efficient. And as I try to emphasize, there's an issue with this kind of k-nearest neighbor instance-based method is, so I think, is it computationally scalable? I will make it really quick. I will not derive this, but I think I have a detailed derivation in the extra slides. Feel free to check out those. Let's compare linear regression versus the k-nearest neighbor-based regression. All right, so linear regression, we actually know its training step. If we do this, the normal equation base, our cost is ONP quadratic plus P cube, and this is the naive version, right? You can actually do a lot of faster, but let's just compare the naive. In the k-nearest neighbor training, it's actually no cost, nothing. In the testing, when you have m equals to 1 samples, what is the cost in the linear regression? It's in fact OP. I hope you understand this, because what we do is y predicted equals to that y w predicted, and W transpose, yeah, let me use beta maybe. Last time I used the beta. Beta transposition x, and x is from RP, and this inner product cost is OP. So for each sample, you have only OP cost. And not to mention, if you have parallelization, this is actually much faster, right? However, let's look at the k-nearest neighbor base. And we already know you have the NP plus the sorting cost, right? Think about when you have n equals 20k, what's the differences of this OP versus ONP, right? So there's a huge problem using the test in the testing mode of this type of instance-based method. So the other thing is, so why do we still use k-nearest neighbor? Why it's so popular? Is it asymptotically sound? So what do I even mean asymptotic? Asymptotic means when you have infinite number of training samples, what is the behavior of your classifier, of your predictor? And this is, you can think about this is almost the upper bound of your predictor. And it's a very good theoretical bound to understand your predictor. Okay, so I did not cover it, but you can think about k-nearest neighbor estimate the conditional probability of that xp y conditional x on at that neighborhood, and you can actually prove asymptotically the error rate of one nearest neighbor classification is less than twice of the base rate, and in particular, asymptotic error rate is 0 if base rate is 0. All right, so this actually proved asymptotically k-nearest neighbor is close to optimal. All right, so there's a reason why people, even though people don't start from this principled reason, but fundamentally it's a good method, and it indeed already had profound influence in many different kind of scientific domains. Yeah, many things we're doing, in fact, are k-nearest neighbor. We just don't name that way. Yeah, so is k-nearest neighbor ideal? There are a lot of slides I put in the extra, and feel free to check out those. So just to give you a quick, because I think this is such an interesting topic. When you're implementing the homework 4, we require you to implement the naive version. But in fact, when your data is large, training data is large, it's like ONP cost, right? Even one sample is extremely slow. And you need to do some tricks. And there are a lot of tricks. I mean, for example, one trick is called KD tree based, and it organizes your training data in this kind of tree. And when you're searching a new future points, you really don't need to look for all the points. You only need to look for it's this region tree based neighbor points. So that's the trick, how you reduce this ONP cost. And yeah, so let me put that, it's ONP, right? It reduced the n into n prime. Okay, So this is all I want to talk today. Feel free to check out KD tree-based nearest neighbor search. It is extremely interesting and very computational flavored implementation method. All right, thank you.